We've seen that conditioning is the way we talk about the sensitivity of a problem. Well, corresponding to that is the idea of stability, which is how we talk about the sensitivity of an algorithm. So another way of thinking about it is that every problem has some built-in sensitivity, but depending on which algorithm we choose, we might introduce some additional sensitivity that makes things worse. It is possible to talk about stability from a rigorous mathematical point of view, the way we did with conditioning, but it's a little bit more complicated than we need to get, and so instead we're just going to stick with a looser idea about it and study it through a long example. So let's consider the case of the intersection of two straight lines described by the two equations we have here. So graphically, right, we have one line that's at a slope of 45 degrees, and another line whose slope is practically zero, although not quite. Okay, so but I have to exaggerate it to draw it, but the slope is actually, incredibly small, and they intersect at a point which you can check is the point 1, 1. So we're trying to find that point of intersection by solving these equations simultaneously. So you go back to middle school algebra to do this, right? So the first method we might choose is to look at the first equation and say, well, we can solve for x in the first equation. We get that x is equal to y, right? So then we plug this value in, right? Substitute for x in the second equation. When we do that, right, then that means we just replace the x in that second equation by a y instead, here. And rearrange that, right, we find that y is equal to this number divided by that number again, 1 minus 10 to the minus 10th from the left-hand side when we factor y out. Okay? And as you would expect, when we do this operation in floating point arithmetic, even though the representation of this particular number on the right-hand side is not exact, it is consistent, so that when we divide it by itself, we get exactly 1. And MATLAB is showing us all the digits here. The result is 1 exactly. And then, of course, now that we've solved for y from the second equation, we go back to the first equation and solve for x using the value of y. Well, we said x is equal to y, so x is also equal to 1 exactly. So we can't do any better than that. We get the exact right solution, even though it's floating point arithmetic. On the other hand, there was nothing necessarily that distinguishes that first equation from the second equation. We could just as well start with the second equation. So from the second equation, we solve for x. Okay, we get a more complicated expression in y. Plug that back into the first equation. Okay, we get this result. So now we have to solve that equation for y. So two numbers go onto the right-hand side, right? These two move over to the right-hand side. And then y is multiplied by 10 to the 10th minus 1. Okay, so again, we have an inexact floating point number. Divided by itself, we get 1 exactly. Right? Now we go back to the second equation. Solve for x. Okay, that's what we had right here. Okay, plug in the value of y that we know, and we get, well, we don't exactly get 1 anymore. We only get 1 to, in fact, this digit's not correct after rounding off. So we only get 1 up to 1, 2, 3, 4, 5, 6, 7 significant digits. The reason isn't very hard to see. By now, we know what must be going on. So when we take a large number, when we take a small difference relative to 1, we can't represent the whole thing very accurately, right? So the result is not accurate all the way out. It's only accurate to these digits here, or we're going to lose these digits here, sorry. So because of that subtractive cancellation, we lost 9 digits. That's why we have only 7 digits left in the answer. Well, you might think from a certain point of view that 7 significant digits is not that bad an answer, and that's true depending on the context. But the truth is that we did lose 9 digits. Furthermore, we didn't have to, because we know from the first method we can get the answer right exactly by using a different algorithm. And what's more is the numbers in this thing are completely made up. If I had chosen, instead of a smaller number, instead of 10 to the minus 10, if I'd chosen, for example, 1 minus 10 to the minus 20, well, there is no floating point number which is that close to 1, so that would actually equal 1 in floating point. And so if instead of 10 to the minus 10 and all these things I had chosen 10 to the minus 20, we would have gotten an answer that had no accurate digits at all. So depending on which algorithm we choose, we could either get the answer exactly right or catastrophically wrong. Well, when we have to subtract 2 nearby numbers, we know we expect subtractive cancellation. There's no choice in the matter. On the other hand, in some problems, maybe we can avoid that step. And that's exactly what happened in method 1. All we had to do is divide a floating point number by itself, here, and then copy that result into x, both of which we could do perfectly. But in the second algorithm, we had a case of relying on subtractive cancellation to make this number try to cancel out this very close nearby number, and because it was everything was happening out in the 10th digit, we had to lose some digits. So the moral of the story is that the choice of algorithm can be extremely important, and when we see, very large growth in the error that's not accounted for by conditioning, we call that instability in the algorithm. And so we're going to have to look for stable algorithms as opposed to unstable ones. Interestingly enough, a lot of times the algorithm that you first learn for a problem to solve it mathematically as though numbers were exact turns out to be unstable when you do it in floating point arithmetic. And we'll see that a few times in the things that lie ahead of us.